Okay, what I want to do is kind of talk a little bit more about another example using the first law and looking at air. Now, we've done some of these equations already. In fact, parts A and B are kind of review-ish. We've done some of this already. We've looked at using the formulas that we'll use for A and B have certainly we've looked at before. But part C is going to be pretty new for us, okay? And so that's going to, well, we're going to get definitely some new concepts and some new things that we're going to be applying for part C, okay? But this is also just a good review. We've been spending a lot of time with water. We spent some time with refrigerant 134A. But another, obviously, critical one we got to look at is air, okay? And so let's take a look at this example here. Okay, first off, it says here, air is expanded in a piston-cylinder assembly from 0.1 meters cubed to 0.5 meters cubed. Assume the pressure remains constant, right? Piston cylinders, we're going to generally make that assumption. 100 kPa, atmosphere, pretty much, right? Okay, if the initial temperature of the air is 27 degrees Celsius, determine the following. Okay, final temperature, work done, and heat transfer. Okay? Now, first thing, when I mention a problem and you're reading this, homework, quiz, test, whatever, and you see air, what do you think should pop in? Yeah, ideal gas laws. Yes. Now, good. Yeah. Ideal gas, because it'd be hard for me to construct a problem. I'm sure I could. But it would be hard for me to construct a problem using air that doesn't involve the ideal gas equation in some way, shape, or form. Okay? It could be done, but it's, unlikely. There's two forms of the ideal gas equation we've kind of looked at. PV equals mRT, and P little v, specific volume, equals RT. Now, I don't know, I've been talking with the other class about an equation sheet. There's so many equations we've had to keep track of. And some of you are saying, look, can you give me a sheet that can help me kind of organize all this stuff? And I'm kind of working on something now that, kind of working on basically the equation sheet you'll have for next week's test. And I thought about this ideal gas law, and I thought, do I really need to give both forms of that? I mean, I think it would almost be more confusing. Hopefully you all can see that the second one there, the second one comes from the first one. All you have to do on the top one is divide both sides by mass, and you get the second one. Does everybody see that? Okay, that's the same. Now, in this problem, which form do you think might be better? I'm hearing bottom.
Well, actually, you got to expand,
There is no mass given. That's true. But what about the volumes? The volumes are given as absolute volumes, though. So, I don't know. I think you could probably work it either way. It's really the same thing, right? But I guess because I see absolute volumes, I'm thinking I'm going to use that top one that has the big V, right? Because I guess I'm thinking that just because I see those volumes given as meters cubed. So that's not specific volume. If I was given specific volume, dead giveaway, I'm going to go for the second one. But I'm thinking the top one, it doesn't matter. I'm sure somebody could say, look, I could use that second version just as fine as you could use the first. Probably true. Okay. So we got that. We'll just look at this top equation. Okay, so PV equals mRT. Now, let's start writing down before we jump into this. We know we have to use the ideal gas. You see air, you just write that ideal gas law down. I got to use it, okay? Now, the next thing I want you to do is start looking and saying, what do we know about each state? We got state 1 and we got state 2. State 1 before, state 2 after. What do I know about the initial conditions, basically, of this thing? Any? I know the volume. Certainly V1 is going to be what? 0.1 meters cubed, right? What else do I know? You know the temperature? The initial temperature, right? T1 is equal to 27 degrees Celsius. But what do I need to do if I'm using ideal gas law? Got to change it to Kelvin, right? Right away, Kelvin. Which, by the way, is 300 Kelvin. Right? When you have air, think ideal gas. And then when you have ideal gas, remember your temperatures need to be in Kelvin, or if we're in the English system, Rankine, right? Okay, and then you know the pressure because the pressure is constant, right? So P1 is 100 kPa, and oh, by the way, P2 is also 100 kPa. And also I know V2, obviously, right? I know the volume afterwards is 0.5 meters cubed. Okay, it seems like I know a lot of stuff, and I should be able to do this, right? I've been given a lot of information, okay? The key to doing this is to manipulate the ideal gas law, okay? And that is, if you take the top form here, okay, PV equals MRT, and you rewrite it as such, you can write PV, okay, over T is equal to mass times R. All right? And then there's just simple algebra. Then the mass, in a closed system, the mass doesn't change, right? The mass is constant. And R is, because of air, it has the same R, right? So therefore, that's a constant. That's a constant. And then you can write the following. P1 V1 over T1 equals P2 V2 over T2. Okay? And I will tell you, there's a lot of cases where you can do that with air and with these type of problems. Not always, but a lot. If the mass is changing, you couldn't do that. Okay? But if it has a constant mass, then you can't. Closed system, you're good. You could wipe those out, yes. Since P1 and P2 are the same, you can wipe them out. What I'm going to do before I wipe them out, though, is I'm going to manipulate this. This is very simple algebra to solve for T2, right? Because that's what I want is T2. So T2, by the way, if I multiply both sides of that equation by T2, and then I divide by P1, V1, you know, do a little algebra here. You're going to get P2 over P1, okay, times V2 over V1, right? Okay, times T1. Everybody see that? Just some algebra, right? I just divided both sides by P1, P1 V1, and multiply both sides by T1. You know, just playing around with it a little bit, algebra. Not too bad, right? Yes, P2 and P1 are the same. So the fraction of P2, if you take P2 divided by P1, that just goes to 1, right? That just goes to 1. And it's very simple to do this. This is easy. V2 is 0.5 meters cubed. V1 is 0.1 meters cubed. T1 you have to put in Kelvin, 300 Kelvin. So you get 1,500 Kelvin for T2. Which, oh, by the way, is also equal to 1,227 degrees Celsius. Yeah, that was a big temperature rise to do that expansion. This air really heated up. It's very hot now. Okay, that problem. All it was is ideal gas. Okay, all it was is a manipulation of the ideal gas law. You should be able to do that. That's not really anything new. Okay, second part. Second part is also very easy and something you should be able to do. Yes. What you have here is the work is equal to pressure times V2 minus V1, and that's because we have a constant pressure process. That formula comes directly from your book, from your notes, things like that. Of course, you'll get it on your equation sheet. I'm not going to label it, go, oh, by the way, there's a constant pressure equation. I'm not going to do that. But it will be available to you, as will all the other work ones we've done. So this is easy, right? This is a quick plug and chug. So this is part B is easy. Okay, so the work, the thermodynamic work here, Okay, sometimes we add the little term B for boundary. It's basically the thermal work. Is 100 kilopascals of pressure times 0.5 half a meters cubed volume minus 0.1 meters cubed volume. If you work that out, kilopascals times meters cubed does equal kilojoules. Prove it to yourself if you don't believe me. And so this answer is going to be 40 kilojoules. Okay, now this last part's really where the new stuff begins. Okay, this is really where we're going to go into some new stuff and talk, kind of get to some new content, some new thoughts and ideas. This other stuff, we basically just applying equations you've already seen before. Hopefully you kind of recall them, right? Okay, the last part says this. Give me how much heat was transferred into that air. Obviously, it had to have some heat transfer, right? The air was initially 27 degrees Celsius, and at the end, once it's expanded, it became 1,227 degrees Celsius. So this air really heated up, right? So obviously, I had to put heat into this thing in order to expand it, to make this happen. And I made work, by the way. My work was 40 kilojoules. That's work out of the system. That's good. That's good. That's the same thing as what you saw that car there. That car, the Lego air power car, you know, that's the work. It's the work of that air that made that engine go. It's the work of this engine here to make this go, right? It's the work of that air that gives you 40 kilojoules. That's useful energy. That's the kind of energy that can make your car go. It can lift an elevator. It could create electricity with that energy. That's useful energy. That's the good stuff. That's what we pay for. So I'm very happy. I created some power, but I had to get heat to do that. So yes, I created energy, useful energy, but I had to put heat in. How much heat did I have to do? Okay. Well, here's the deal. Remember what I said about heat transfer. How do you calculate heat transfer? Does anybody remember? This is not heat transfer course, so there's only one way we can calculate heat transfer. What's that? First law of thermodynamics. Exactly. That's the only thing we got. Okay, so if I ever ask you for heat transfer, the only thing you got, so all I got is the first law. Okay, and the first law is going to say Q minus W is equal to U2 minus U1. That's big capital U, capital U2, capital U1. Okay, plus of course the kinetic energy term plus the potential energy term. And you can tell I'm kind of lazy. I don't even bother writing the kinetic and energy, potential energy terms. Excuse my laziness. Because we cancel them out a lot of times, right? We assume they're small, okay? Okay, so that's big U, big U2, big U1. Now, I'm going to simplify this, of course, by saying, no kinetic energy, no potential energy, right? And let me manipulate this. I think you all agree with me, right? That I can just put the W to the other side. That's not crazy, right? And then big U2, big U1, I'm going to do that. I'm going to change that a little bit, and I'm going to rewrite this like this. I'm going to say it's Q is equal to W plus the mass times little u2 minus little u1, like that. Where the little u1, u2, that is going to be like the internal energy per mass, right? Okay? I try to make my little u's small and my big u's big, so you know the difference. One's per mass and one's not. Okay, well, let's fill in what we know, or let's figure out what we can get here. We've got the work, right? The work is 40 kilojoules. That goes right there. So we got that number. We got that. That's 40 kilojoules of work. We know that. So that's going to be 40. How do I get the mass? How do I get the mass of the air? Look up specific volume on a chart. Since I know the volume, I can look up the specific volume. It is possible to do that, but do you see anything there that might point out how to solve for mass? I make it easy, don't I, right? Couldn't you just use the ideal gas, right? Okay, now the reason why I say not to use the charts for specific volume, I will explain in just a few minutes, okay? Because I don't know about you, but have you guys even looked at the air charts?
It doesn't give you specific volume.
Yeah.
I tried doing
Yes,
it.
yeah, the air charts don't even give you that stuff.
It's annoying.
Yeah, it's annoying, but it gives you something. But it's like, what is that? We'll talk about that in a moment. So when it comes to air, the more you can use the ideal gas equation, the better, okay? Just don't do that with water, okay? Don't do that with steam, water. Don't do that, okay? Air, all right? So here's the deal. All you have to do is take PV equals MRT. I think you'd all agree with me that if you want to solve the PV equals MRT for mass, right, isn't it just PV over RT equals M, right? Isn't that it? It's not that hard. It's just another algebra, okay? That ideal gas equation is your friend. Use it, use it, use it. It's not that hard, right? You do it a couple times, you go, oh, this is easy, right? It's just algebra. Okay, so let's do that. Since PV over RT equals M, I maintain I can solve for M like this. So I'm going to just rewrite this. PV over RT is equal to M. Okay. So what's my pressure? Now, I could use the initial states or the final states. Let's just go with the initial states. Okay. So my initial pressure is 100 kPa, right? That's the same as the final pressure. My initial volume is 0.1 meters cubed, right? My R for air, the R for air, the ideal gas equation for air, ideal gas constant for air, is 0.287, which I have memorized enough, but it is in your tables. It is actually table A1. It's the first thing in table A1, air. It's the ideal gas constant for air. It turns out to be 0.287 kilojoules per kilogram K. By the way, it's so important, I'll probably put it on your formula sheet too. Okay? So, but if I give you a different thing, I have seen students in the past where if all of a sudden I pull the rug under them and instead of air, I say it's helium or something like that, they freak out. Okay? There's no reason to freak out. The only difference is the R value. Okay? That's it. There's nothing else that's different. All right? So don't try to make it any weird if I give you helium or nitrogen. Well, nitrogen's pretty close to air. If I give you some weird thing, it's the same process. I just changed the R. Okay. And then the temperature, you have to use the initial temperature, which is 300 K, right? All right. Now, if you take a look at those units, you've got kilopascals times meters cubed divided by kilojoules per kilogram K times K. I think anybody can visually inspect that, and obviously the answer is in kilograms, right? No, I joke. It's probably not that easy for you to see that the units work out to be kilograms there, okay? They do, all right? And by the way, notice you have kilopascals on the top and kilojoules on the bottom, so the kilo kind of cancels the kilo over kilo. And so they kind of cancel. And the kelvins cancel here. If you work this all out, a Pascal times a meters cubed, that's going to be like a kilojoule. The kilojoules, it all cancels out. Okay? So the answer is actually in kilograms. Okay? And it turns out to be 0.116 kilograms. So that's how much mass we have. Okay? So let me just kind of reframe this. Let's just say if I want to solve for the Q, it's equal to 40 kilojoules plus 0.116 kilograms times U2 minus U1. And again, the answer is in kilojoules here. So this is where it leads me. I've got to get U2 and U1. Okay, I've got to get the internal energy of air. Okay, I've got to get the internal energy of air, some way, shape, or form. All right, there's two ways to do it. There's two ways to do it to get this. So the question now is, what is U2 minus U1? Okay, what is that? Well, the one way you can do it is to use the tables. Okay, now we haven't done this yet, but let's do it now. Let's look up U1 for air at a temperature of 300 Kelvin, and we're also going to look up U2 for air at a temperature of 1500 Kelvin. We do have tables for that. Okay, so you got to go open up your thing here. Find our handy dandy tables right there. And you got to scroll along. It's not right away. It's kind of in the middle. Oh, here we go. It's table A17. Table A17. The ideal gas properties of air. Okay? Zooming in a little bit. First off, I want to mention, as has been mentioned already, take a look at the stuff on the top there. Look what's given to us. You have got, the H and the U are very clear, okay? H, of course, is enthalpy. That's given in kilojoules per kilogram. And U, which is internal energy, which is what I want, right, is given in kilojoules per kilogram. That's great. I'm really happy with that. But notice the other terms here. What's PR and VR, okay? What kind of units are that? I thought pressure, it doesn't give me any units. Look, it just says PR, and it just says VR. I thought pressure was units of newtons per meter squared. I thought VR, is VR specific volume? I thought that was units of meters cubed per kilogram. What is that? Okay, that's like what we call a reduced pressure and reduced specific volume, okay? That's something that we may get into later, but we're not going to use it right now, okay? What we're going to do is when we want to calculate pressures and volumes, we're not going to use this table, okay? We are going to go to the ideal gas equation, okay, to do that. This table is only going to be used for our H's and our U's, in this case U, right? In fact, we can clearly see the first U we want, the U for temperature of equal to 300 Kelvin, right there, 214.07, right? So we'll fill that in here, 214.07 kilojoules per kilogram. So this first U is 214.07 kilojoules per kilogram. We looked it up off the table, right? Okay, let's go to the next one. The other one is 1500 Kelvin. So for that one, for 1500 Kelvin, it's on the next page. It's going to be 1205.41, right? 1205.41 kilojoules per kilogram. 1205.41. Okay. All right. So it turns out, in this case, U2 minus U1, if you just do this subtraction there, that's not much of a subtraction, right? U2 minus U1 is 991.3 kilojoules per kilogram. Okay? So we got everything. We got everything we need. If you go back to this equation, I'm done, right? If you go back to that equation for Q, I got it all. I got U2, U1, everything. I can just calculate it, I'm done. But I want to do, before I do that real quick, I want to talk to you about this because there's another way to do this. How else can I get the difference in internal energies, U2 minus U1? There's another way that's going to be important, and we're going to talk about it even more on Tuesday, but we're going to start today. I've already talked about it last week a little bit. Anybody remember? What's another way to get the difference in internal energies besides using the tables? I haven't used it a lot yet, so maybe that's why you don't remember. But it's going to be critically important in a lot of applications. Anybody? It's 2 words. The second word is heat. Specific heat. Yes. Yeah. We can get U2 minus U1 by applying, you can also get it using specific heats. Yeah, that's one thing. If we go off the table, then you're done then, right? The temperature gets too high. You have to use specific heats. Yeah. You'll find in practice a lot of engineers like to use specific heats because it simplifies things. Okay, you don't have to use the tables. You can just bang it out pretty quick. You can get the answer. Okay. So how do we get that? Well, remember, here's the deal with gases. With gases, we really have 2 formulas we need to learn, okay? And that is, we have with gases, we have U2 minus U1 is equal to C sub V, T2 minus T1. And then we have H2 minus H1 equals C sub P, T2 minus T1. Unfortunately, we couldn't keep it easy. We have to make this more complicated. You have to have, there's not one ideal gas for, so there's not one specific heat for gases. Okay, there's always 2, C sub V and C sub P. Okay, the C sub V can be used to get the change in internal energy. The C sub P can be used to get the change in enthalpy. Now, one of the biggest questions I always get from students is, how do I know when to use U's and when to use H's? And the answer is fairly simple. If you have a closed system, you use U's. If you have a control volume, you use H's. But remember, we haven't done much with control volumes yet. We don't have open systems yet. Almost everything we do right now has been a closed system. Okay? In fact, when we get past the test next week, we're going to start doing control volumes, open systems. Okay? But for now, we're going to focus on just the change in U, and that comes from C sub V. Okay? C sub V times change in temperature. All right. So then, okay, this looks easy. So you want me to get U2 minus U1. By the way, you can't use specific heats to get the actual internal energy. You can only get the change. Okay, so it's going to have to be the C sub V times my temperature change. Well, my temperature change is pretty simple, right? I went from 1500 Kelvin, it went to 1500 Kelvin from 300 Kelvin, okay? And by the way, the change in temperature, it doesn't matter whether you're in Kelvin or Celsius. It's the same change, right? It's the same change, okay? So all I need to do is look up my C sub V. All I need to do is look up my C sub V. So I got to go to my tables again. My tables will give me the C sub V for air. Okay? So we're going to go there. Now the thing is though, oops, I got to go kind of to the front of the tables. Okay. Here we go. Let's go to table A2. Okay? Table A2 has, it says at various temperatures, it gives me the C sub V for air. Now notice that my 300 is given. For 300, my C sub V is 0.718. But what about my 1500? It's not on the table, right? It's not there. So what do I do? And I'm supposed to only use one C sub V, not like a bunch of values of C sub V, right? So what C sub V should I use? What would be a logical choice of C sub V values to use if you're going from 300 Kelvin to 1500 Kelvin? Halfway between, I like your thinking. Yeah. Why don't we just go halfway between? So if we're going from 300 Kelvin to 1500 Kelvin, what's halfway? 900 Kelvin. 900 Kelvin, right? 900 Kelvin is halfway between 300 Kelvin and 1500 Kelvin. So a logical choice for C sub V would be to use halfway. Okay, let's just use this value, 0.834. Okay, let's use 0.834. It's halfway. That's probably a good average value for C sub V between 300K and 1500K. I'm glad it's on my table. Okay, so we're going to use 0.834. So you're going to do, just put it in here. It's going to be 0.834 kilojoules per kilogram K multiplied by 1500 minus 300, and that's going to give me U2 minus U1. If you work that out, you work out the math, I believe you get 1000.8 kilojoules per kilogram. So do you think there's pretty good agreement between this formula and what the tables told us for U2 minus U1? Pretty close, right? The tables told me 991. Using specific heats, I got 1000.8. I'm pretty happy with that, okay? Remember, this is thermo. If we're within a few percent, we're happy, okay? We're not trying to get everything perfect. Yeah?
The specific heat is above your temperature on there, like you got 200,
Mhm.
about
Yeah.
200,000, you still go between.
Yeah, I would still use the average. You always try to use the average between them. Yeah, that makes the most sense. Yeah. Yep. 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 Okay, so now we have two ways of doing this. We can use specific heats, or we can use the tables. Now, I will tell you that if you have tabular data, you always want to try to use that. Okay, it's going to be better. But in many cases, you don't have tabular data, or you're just trying to go quick. You're trying to quickly get things done, and specific heats are a good way of doing it. All right. So one more thing, real quick here. Let's actually get the number. Okay. Let's actually get the number. Here it is. We got to substitute U2 minus U1. Since I told you tabular data was better, let's use 991.3. So we're going to say this. Q is equal to the 40 kilojoules of work, right, plus 0.116 kilograms times 991.3 kilojoules per kilogram. Can someone calculate this number for me? So about 155 kilojoules. Good. Okay, now let's think about this in context before we move on. Here's what's going on. Here's what's going on. This is our system. Okay, whatever. I'm just drawing an arbitrary box here for our system. Our system gave us how much work? How much work did we get? 40 kilojoules of energy. 40 kilojoules of work. That's what we want. We want work. Work is good. I don't want to put work in. I want to get work out. How much heat did I have to transfer in to get that work? How much heat did I have to put in the system to heat up that air to give me that 40 kilojoules of work? 155 kilojoules. So I put 155 kilojoules of heat into that system. I got 40 kilojoules of work out of that system. Where did the other energy go? What happened to the other 115 kilojoules of energy? Poof, disappeared? What? It goes back out as heat. Yeah, we lost it. It was like wasted heat. Okay? So the other 115 kilojoules here was wasted heat. Okay? called waste heat. Okay. This is heat in, and this is work out. That's the next great question. We're not going to do that because you're talking about a Chapter 6 question. I'm just introducing it right now in Chapter 4. But this is really a good question. That is this efficient or not? Is this good? Do we like this kind of efficiency? You might say no. You might say, yeah, I don't know if you do. But I'll tell you this. If you're talking about cars, this is good. Okay? Because, or pretty good, I'd say, because you're getting 40 kilojoules of energy, you're putting in 155 and you're getting 40 out. That's not bad. Cars waste a lot of heat. Yeah, try touching your engine. You know, there's a lot of heat wasted, okay? So this is not that bad, okay? It's not great, but it's not bad, okay? It's not bad at all. You might think, oh my gosh, I had to put 155 kilojoules of heat in just to get 40 kilojoules of work out? Yeah, I did. But remember what I said the first day of class. Heat is cheap, work is expensive. Heat is cheap. I can make heat pretty quick. Heat is easy to make, okay? Heat is cheap, work is expensive, okay? We want this. This is the whole point of thermodynamics in most part, is to get useful energy. The energy that drives our car, that flies our planes, that powers our electric grid, that's work. That's the useful stuff. Heat, you know, besides a cold winter night, doesn't help me too much. Of course, it is appreciated in a cold winter night. But other than that, you know, don't need it too much. Okay? It doesn't do anything for me. Okay? It's energy that doesn't do anything until I make it do something. And that's what this engine does, basically. This is basically an air engine. Okay? This introduced the concepts we're going to get into later that are going to be very important for us. But I thought this was kind of nice because it just kind of shows it. And by the way, this is a real system. You could build this, and you could do it. You could put air, right? It's air at 100 kPa. That's standard air. And you could build a piston cylinder, buy one that has this amount of air, and then you could burn something, right? A fuel, right? And then you could heat the air up. It could expand, and that could give you work. It could give you energy. I mean, you literally could do this. Okay? It wouldn't be that hard to do. Okay? You could make your own little heat engine. Okay? That's what this is.